discussing the mathematical operations through amplifiers, and op amps are used in this process, and in fact that is the reason that why these are called operational amplifiers. So, the mathematical operation which was currently under discussion was a summing amplifier, a scaling amplifier and an averaging amplifier. These are three different amplifiers, but because they all the three can be drawn from the basic amplifier. So, that is why I am taking them all under single heading. Now, these amplifiers can be realized by using a inverting amplifier, inverting op amp, or by non-inverting amplifier equally well. We are taking just one case, that is of inverting amplifier. So, how to realize a summing amplifier with inverting configuration? The summing amplifier is the one in which the output is the sum of all the inputs. I repeat that summing amplifier is the one which gives a output which is the sum of all the inputs. This is summing amplifier. Now, the inputs can be more than one. So, maybe 2, 3, 4, 5, 6 or it can be number 8 or 10, but we just to make the diagram simpler, we take 3 inputs, and when we use a inverting in configuration, then this circuit is this. V1, V2, V3 are the 3 voltages which are to be summed up, and output is here, and this non-inverting input, normally so far we have been putting at a ground potential by directly grounding it, but for the better arrangement is when this resistance R x equivalent to the parallel combination of these resistances is attached. It is still at ground potential, but not directly, but through a resistance, and this reduces the offset effects. We have not yet talked about the offset effects. We will talk little later about these things, but they arise because of the asymmetry in the design of the circuit, and even when the inputs are absent, some currents still flow. They are of course very mild, very small currents, but still. So, those offset effects can be reduced drastically if instead of directly connecting the non-inverting input to ground, it is connected through a resistance equal to the parallel combination of all the input resistances. Now, here this is at a potential V B, and the 3 currents I1, I2 and I3, they flow here, and from here will flow IF. Now, remembering that VV is at 0 potential. Remember, we have said that the inverting input is virtual ground. So, this is at ground potential. Hence, VB is 0. If this is so, this voltage is 0, here it is V1, then we can simply write the expression for the current I1. This is actually speaking V1 minus VB by R1, but because V is 0, so I1 is simply V1 by R1. Similarly, we can write for I2 and I3. So, I2 is V2 R2, I3 is V3 R3. These are the currents. And now we are seeing that this is simplified and the whole expression gets simplified by this concept of virtual ground, and that is why emphasis was given to this point that the inverter input is inverted input is a virtual ground. Now, these three currents are flowing. There will be a current here IB, but IB, as we are seeing that because the input impedance of the amplifier is extremely high, so this IB can be taken as 0. IB is equal to 0. We neglect this current, it is extremely small current. It is extremely small current. If we neglect this current IB equal to 0, then obviously the summation of these currents is equal to IF. Therefore, I1 plus I2 plus I3, this is equal to IF. And we can write for IF all the three currents we have written. We can also write for IF the current we can write right here. These three currents we write. Now, what will be IF? IF, this is VB minus this terminal is at potential VB, which is 0. We will write finally 0 minus V0 by RF, and this is equal to minus V0 by RF. So, substituting the values of all the currents in this expression, we get V1 by R1, which is equal to I1, plus V2 by R2 plus V3 by R3, and this is equal to minus V0 RF. Or the output we can write from here, or V0 is equal to minus RF R1 by V1 plus RF R2 V2 plus RF R3 V3. This is the relation which is, we may say, the basic relation for this circuit. And then by choosing, you recall that RF by R1 is the magnitude of the gain by which V1 will be amplified. Similarly, RF by R2 is the gain by which V2 will be amplified and it will appear at the output and so on. So, for now from this basic equation, which we may call as first equation, we can now go for summing amplifier. Summing amplifier. In this equation 1, if we choose R1 equal to R2 equal to R3, say this is R, then what we have is this: V0 is equal to minus Rf by R and V1 plus V2 plus V3. If further we choose Rf, this gain, as 1, so Rf, further if Rf is taken equal to R, then gain, magnitude of gain is equal to 1, and in that case this term will be 1 and V0 is simply minus V1 plus V2 plus V3. That means the output voltage for this summing amplifier under these condition of choosing R1 equal to R2 equal to R3 and let us say that is R, and Rf also equal to R, that is all these resistances in this circuit are taken as single value resistances. All these resistances Rf, R1, R2, R3 are taken as a single value resistor, say 10K, 20K and so on. Then the output will be the sum of all the input voltages with a reverse sign, with a negative sign. That is, sign is not really material. If we want positive, we can use the sign changer circuit after that, which we have already discussed. And in the, because this minus sign is coming because we have taken a inverting amplifier. If we take non-inverting, this sign automatically will disappear, but as I said, it is not a significant point. So, this is the summing circuit. Then we can go for a scaling or weighted amplifier. Scaling or weighted amplifier. In the simple summing amplifier, we have seen that all the inputs are amplified by the same amount, choosing all the resistances as single value R and Rf also of R, then a simple summing amplifier results. A scaling or weighted amplifier is the one in which the inputs are, each input's voltage is amplified differently. I repeat that in a scaling amplifier is also called weighted amplifier, in which the amplification factor for individual input voltages is weighted, is not same, but they are different, they are weighted. And so then the amplifier is called a scaling or weighted amplifier. Such amplifiers are needed. For example, if we want that the output should be when V1, V2, V3 are the input voltages, then the output should meet this requirement. That means this equation should be satisfied. This is a equation. The output should be according to this equation, where V1, V2, V3 are the inputs. Now here same circuit and same fundamental equation, the circuit is the same, but here the values of R1, R2, R3 and RF we have to choose differently, and we will take help of this basic equation which we have written for that amplifier. Now in this case, if we choose a particular value of RF, for example, let RF, the feedback resistor is of the value of 12 kilo ohms. We can choose 24, but just as an example I am taking 12. Then we should choose R1 as 3K, 3 kilo ohms, so that this will be amplified by RF by R1. Look here, RF by R1 into V1. Here we want a factor of 4 according to the requirement, and if we choose RF at 12 kilo ohms, then R1 necessarily we will have to take at 3, so that a factor of 4 comes, and R2 we are supposed to take as 24 kilo ohms, because RF by R2 here we need is 0.5. So this will be 0.5 when 12 kilo ohms divided by 24 kilo ohms. So that means 12 by 24, which is 0.5. So we will get a gain of 0.5. And similarly R3 we take as at 8 kilo ohms. These resistances are all different. R1, R2, R3, they are not same, they are all different, and they are different than RF as well. So this scaling can be done according to this equation by choosing these resistances, and then keeping that we will get, which will be 4 V1.4 V2 plus 1.5 V3 with a reverse sign, with a minus sign, and this minus sign we have already talked, it is not really much important, it can be taken care of without much problem. So this is the scaling or weighted amplifier. Then the third one was the averaging amplifier. Averaging amplifier. What's a averaging amplifier? Averaging amplifier is the one of the inputs, average of all the inputs put together. So that is averaging amplifier. Now averaging amplifier, again by the same fundamental equation we can get, if R1 is equal to R2 is equal to R3, say R. If this is the condition, and RF by R is taken as 1 by n, this is additional, This is additional point. First point is this is the second point, and Rf by R should be taken as 1 by n, where n is the number of inputs. In the present case, which is under discussion, there are 3 inputs. So, this factor Rf by R should be equal to, in the present case, under discussion, we should have Rf by R equal to 1 by 3. Now, if we substitute Rf by, when we take R1 equal to R2 equal to R3 equal to R, so here this is common term which we can take out, Rf by R, and Rf by R in this case is taken as 3. So, obviously V0 is minus Rf by R into V1 plus V2 plus V3, and since this is taken as 1, so V0 will be minus V1 plus V2 plus V3 by 3, because Rf by R is 1 by 3. So, this is the result for averaging amplifier. The output is the average of all the inputs and with a sign reversed. So, this is the averaging amplifier. We continue with these amplifiers. We will take other circuits also, and we continue. Let us talk of a logarithmic amplifier. Logarithmic amplifier. Logarithmic amplifier is the one in which the output is the log of the input. I repeat, what is logarithmic amplifier? Logarithmic amplifier is the one in which output is proportional to the log of input, let us say Vi. This is the logarithmic amplifier. Now, if in the simple inverting amplifier, if we replace the resistance Rf by a diode, what will be the circuit? This will be the circuit. V out, and this is a DC voltage, Vs, DC source, this is the circuit of a logarithmic amplifier. Here the IV characteristics of diode, we remember that I equal to I0 exponential V Q by KT minus 1. This is the equation of a diode which describes the current voltage relationship. This is the applied voltage and this is the resulting current, and here I0 is the saturation current. The saturation current. This we are going to use, and here this KT by Q, this is Boltzmann's constant, this is temperature in Kelvin, and this is Q, the charge, electronic charge. So the thermal equivalent of the room temperature, the voltage equivalent, this is that, the voltage equivalent of thermal energy at room temperature. This comes out to be roughly 26 millivolts at temperature T equal to 300 degrees Kelvin. 300 degrees Kelvin. So as long as this V applied field is say of the order of 500 millivolts or 1 volt, this 1 can be neglected because this is exponential term which will rise very fast, and so neglecting that 1, we can use the equation I equal to I0 exponential V Q by KT. From here, or exponential V Q by KT is equal to I by I0, or we take log of both sides, V equal to KT by Q into log I minus log I0. And this current I here in this circuit, this is Is from the source, this current, and this current is I, and this voltage across this which we are applying, that is V, and this current, the current here, this is actually 0 because of very high impedance of the operational amplifier. The current going in the inverting input is 0. So taking I as Is equal to Vs by R, and further neglecting a small contribution, this contribution of this term is negligibly small. So we neglect that. In that case, this V will be equal to minus, it will be V0, because see here, this is the voltage developed across this, and because it is inverting, so with a minus sign it will be KT by Q into log Vs by R. Thus, this is a constant. So, the output voltage is proportional to the natural log of the input Vs. Output voltage is proportional to the natural logarithm of the input voltage. This is the logarithmic amplifier. Now, we will go for other mathematical operations using these op-amp circuits. We go for the integrator. The integrator. This is also called integration amplifier. Integration amplifier. Here the output voltage is integral of the input voltage. Output voltage is the integral of the input voltage, then the amplifier is called, the circuit is called the integrator. Integrator can be easily realized by using the op-amp in the inverting mode and by replacing the feedback resistance Rf by a capacitor. So, the circuit of the integrator, the basic circuit is this. This is R, this is that capacitance, this is the point X, and here we attach the input signal and output is taken here, V out. This is the circuit. Rf has been replaced by the capacitor C, and here this is the current I which will be flowing, and here also because this current we will be taking as 0. So, the same current will flow here in the capacitor. Now, from the simple basic capacitors theory, from the basic capacitor theory or theory of the capacitor, the voltage developed across the capacitor and the charging current have a relationship that I is equal to C d V by dt. If this is the relationship between the charging current and the voltage developed across the capacitor. This is simple relationship. The charging current gives a rate of change of voltage and the capacitor is charged. Now, applying this equation in the present case, then it will be, let us say, which of course this voltage is V2, which is 0 of course, but for the sake of the argument this is C into d V2 minus V0. the two sides of the capacitor. One is at a voltage of V2 and the other end is at V0, and this is dt. But V2 is 0 as it is virtual ground. Virtual ground. So I is equal to minus C dV0 by dt, and I, this is the same as this I, so I is obviously here Vi minus V2 by R. I is equal to V1 minus V2 by R, V2 being 0 is equal to Vi by R. This is I. So this I we substitute in this expression. Therefore, we get Vi by R, the current, is equal to minus C into dV0 by dt, or from here we can write or dV0 by dt is equal to minus 1 by RC into Vi by dt. Integrating both sides, we get V0, sorry, this will not be there. When we take this, simply this will be the case. So V0 is equal to minus 1 by RC integral 0 to T Vi dt plus C1, where C1 is a integration constant. C1 is a integration constant and represents initial capacitor voltage at t equal to 0, and it represents initial voltage at capacitor at t, the time equal to 0, and this we can set C1 can be set to 0. In that case, V0, the output voltage, will be 1 by RC to integral Vi over dt. This is the expression for the output voltage, and the amplifier therefore provides an output voltage which is proportional to the integral of input voltage. Output is proportional, this is a constant RC, time constant of the circuit. So V0, the output voltage, is proportional to the integral of the input voltage. This is integration, the integrator or integration amplifier. Now let us discuss furthermore and what are the problems in this basic integrator and how we take care of those things. Now, here if the input voltage is constant, if the input voltage is a constant, that is V I is a constant, say let us write with capital V, then by substituting that in this equation we will get V0 will be V t by R c. So, from time 0 to time t, this will be keeping on changing. So, it will be a ramp, the output will be a ramp because of this negative sign, it will be going this way. This is time and this is the voltage V0. So, a constant input voltage, if it is positive, the ramp will be like this. If Vi is a negative voltage, then the ramp will go in the other direction. This is T, so this will be the ramp. This is V0 versus T. And for a square wave input, we will get a triangular shape output. If the input is a square wave, the output will be triangular. That means these ones. This is input, a square wave, this is time, then the output, this is constant, so it will be a ramp, and then this is also constant, it will be a ramp, and these two ramps will be going in opposite direction. This is T, so this is the output, a triangular. So, if the input is a square wave, output is triangular. A square wave input will give a triangular wave. And if the input is a sinusoidal signal, let input voltage be sinusoidal, say Vi is A0 sin omega t. If we put this in the fundamental equation, in this equation, then V0 will be minus 1 by R C into A0 sin omega t dt, and this V0 comes out to be A0 omega R C cos omega t. Here this is important, that the maximum amplitude of the output will be frequency dependent. This is frequency dependent. Therefore, whatever is the maximum output for a signal of frequency, say 1 kilohertz, at 2 kilohertz it will be half, maximum output will be half. So, it is frequency dependent. frequency dependent maximum output voltage. Now let us talk, we continue with the integrator amplifier, that what are the problems with the basic circuit which we have drawn simply by replacing RF by a capacitor C. Now there are two problems with basic integrator. The problems are that for V1 when it is 0, the integrator acts as an open circuit for DC. You look at this circuit. Here when Vi is 0, then in this circuit this the integrator acts as a open circuit, because this capacitor will act as a blocking capacitor and it will not permit any DC currents to be fed back to the input. I repeat that when Vi is 0, capacitor C blocks DC current, and from where these currents will come? These are drift currents, drift and offset currents. I said about offset currents we will be talking later, but at least for the time being we can say that offset currents are there because of asymmetric design of the circuits, which are almost impossible to get them in perfect matched conditions. So these small currents, they will be blocked by the capacitor, and these currents will not be fed back to the inverter, but they will continuously charge the capacitor, and hence the voltage gets developed, and then it is amplified and a output voltage appears while the input is 0. So this presence of this output voltage, it is a error voltage, and it should not be. When input voltage is 0, the output voltage should be 0, but it will be finite because of the charging of the capacitor, and then that voltage is amplified by the circuit, and there will be a error voltage, gives error voltage at the output. Another problem, that in this circuit at very low frequencies close to, for example, 0, the gain of this inverting amplifier is impedance of the capacitor divided by RF by R. RF is now replaced by XC, that is the capacitive reactance of the capacitor. So the gain is this, and this is close to this is very high reactance, because the capacitor 1 by omega C is the reactance. So when omega approaches 0, this reactance XC approaches infinity as omega approaches 0. So that means the gain will be very high for small frequencies. These problems can be taken care by attaching a resistor RF with the capacitor, and that is the practical circuit. Practical integrator. Practical integrator. The circuit is this. CF is that capacitor, and V0 we take here. Now this RF will take care of the problems which we have discussed, that it minimizes RF minimizes the output error voltage. And it will also take care at very low frequencies the gain will not be infinity, it will be at very low frequencies, that means omega going to 0. Now this is infinity we can neglect because RF is in parallel, and gain will be RF by R, which is finite, and we will see that normally this is kept around 10 by design. We keep it around 10. So this takes care, but it puts a limitation. Integration will be, true integration will be there when the combination RF and CF produce a capacitive impedance. Capacitive impedance. And so there is a restriction that at very low frequencies this circuit will not be a true integrator. And what is that condition we will just see. But this is the practical circuit, and inclusion of RF that gives the modification on the performance. Now we discuss the gain, magnitude and frequency response of this circuit. Frequency response of the integrator. Frequency response of the integrator. If we take Vi, we have done it above as sin omega t, and V0 is minus 1 by R CF into, this is omega A0, integral of this A0 into cos omega t. This is input and this is output after integration, and if we take the ratio of the peak voltages, V0 peak and Vi peak voltages, ratio of peak voltages then this is A0 omega RCF, and this is 1 by omega RCF. So the gain, then this is gain falls here. This is V0 by Vi by taking the peaks. This is gain, and this is in dB. This is frequency F, and this is F1, and we will see what it is. This will come out from here. F1 comes out to be 1 by 2 pi R1 R, that we are taking only R, CF, and this has a slope minus 20 dB fall per decade of change of frequency. So this is the frequency response, and this is for the basic amplifier, basic integrator, and how this is modified for the case of the practical integrator. We will take further and discuss other circuits also.